Can't even sing.
I do. See if there's any extra ones.
Who's the idiot?
Thank you.
Yep.
Who's the idiot?
Alright, if my memory serves me correctly, we were in the process of completing number 3. Is that right? Did we finish it? No. How far did we get? Were we making our table? Alright, let me get up to speed here.
I really like the King's skit. Yeah. They did that with the Grand Warden one too.
There's a constant. There's oh, but how do you determine like how many there are? Yeah. There's also one. I mean, you can always just divide it by 0.
All right, we got as far as the table. Was that right? Yeah. Okay, let's go ahead and graph it just to see. So we had 2 possibilities of where the x-intercepts are located, or the types of x-intercepts we have, like positive, negative, 0, imaginary. Let's see which one is correct. So y equals, we'll clear out anything that's in there. Let's see, my window's set negative 10, positive 10. I think that should be fine. Rough picture. All right, of our 2 combinations, which one's correct? The second one. All right, we don't have any positive x-intercepts. We only have 1, negative 1, and if our degree is 3, that means the other 2 that we're missing must be imaginary. Looks good. Do you guys think you can do 4 and 5? Yeah? Go ahead and try them. I'll do them up here so you can check your work as you go. But see how far you can get without looking. When you did number 4, did you only get 1?
Yeah.
Yeah? Okay, just want to double check to make sure I'm not going crazy. Alright, so if that's the only one, maybe you don't even have to graph it. I mean, you can, just to confirm, okay? But if there's only one possibility, we automatically know where the x-intercepts are. 1 positive, 1 negative, and 1 at the origin. How did we do? Good. Do we got to go over any piece of those two? We sure? All right. So we're going to take a look at these imaginary x-intercepts a little bit more today. So when you flip the page, we're going to shy away from graphs a little bit and take a look at an equation approach or an algebraic approach. I want to practice, and maybe you've done this before, maybe you haven't. I want to see if we can figure out what the equation would be, what the equation would look like when we have an imaginary root. So for instance, if you look at the top, it says, suppose a polynomial function has roots of -1 and 2i. So we know that one of the roots is imaginary. We're going to try to create the equation that would fit these descriptions. So we're going to take a root and then convert it into an equation somehow. We've done this before, we just haven't done it with imaginary roots. So that's why it could be a little different. Before we actually dive into it to find the equation, can we anticipate what type of function we should have? Can we name it? If we have these x-intercepts, or roots, or zeros? Quadratic, cubic, quartic. They didn't say that. Suppose that a polynomial function has roots -1 and 2i. How many roots did they give us? 2. Well, they specifically said 2. So we might think that it's quadratic, right? Power of 2. But there's something that we discussed yesterday with these imaginary numbers that's pretty important. Yeah. The imaginary always has 2. You have that buddy system. Okay, they always show up in pairs. So if the imaginary root they give us is technically 0 plus 2i, can we write what the other imaginary root would be? The one that they didn't specifically state? X equals, remember it stems from the quadratic formula. You have that plus or minus. So the other one would be 0 minus 2i, which would just be technically negative 2i, because you don't have to write the 0 if you don't want to. So they specifically give you 2, but since one of them was imaginary, you know that there's a buddy root. Okay, they have to show up in pairs. So it looks like actually altogether we'd have 3. So we'll say 3 roots means cubic function. So when we actually find the equation, we know that the highest power that we have should be a 3. Let's see if we can actually find it. Now it says is that integral? Integral? There should be integers. An integral is a calculus operation. It's kind of a long S. I think I was in calculus mode when I typed that. Okay, should be integer coefficients. All right, so let's see if we can make the connection or translation here. If we know that we have an x-intercept at -1, can we write what the related factor would look like? X plus 1. Okay, now don't overthink this. If we have an x-intercept of 2i, okay, imaginary, can we write what the related factor would look like? Yeah? Well, we're going to have both. So if we have a root of 2i, we would need x minus 2i. And if we have another one of negative 2i, we'll need the plus 2i. So 1 minus 1 plus. It works just like regular real numbers would, okay, but now they're just imaginary. So what we're going to try to do is expand this so we get integer coefficients. We're basically going to turn it into standard form. We're going to multiply everything together. What I recommend doing is multiplying the imaginary factors together because something interesting is going to happen, and we'll kind of see what that is in a second. So if we do the FOIL process on the two imaginary roots, we'll have x times x, which would be x squared, and then x times 2i, so you can write that as 2ix. The order doesn't matter because you're just multiplying them anyway. The insides would be negative 2ix. And then for the last terms, we're going to have a negative times a positive, so that's negative. 2 times 2, which would be 4, and I times I, we can write as I squared. Just like x times x would be x squared. Do we see anything that might simplify here, now that we multiplied together the two imaginary factors? What do you think, Lainey?
2ix cancels out.
Yep, one's positive, one's negative, so those are gone. Okay, and I'm curious if we know anything else. The hands go. What do you think, Olivia?
Doesn't I squared equal -9?
It does. How did you know that? That's good. Mr. Jones, okay. Do we know what the imaginary number is defined to be? Did you just say that?
Yeah.
Sorry, go ahead.
The square root of -1.
Square root of -1. Okay, so that's why, for instance, if you take the square root of -4, you can rewrite that as the square root of -1 times the square root of 4. So square root of -1 we write as I, and square root of 4 we know is 2. So square root of -4 would be 2i if you want to rearrange them. Okay, they're being multiplied together. So if I is the square root of -1 and you square this side, that means you can square the right-hand side as well, but that would get rid of the square root. So you're left with -1. So what's nice about this foiling process, at least with the i's, is whenever you have an I squared, you can simply replace it with -1, because that's what it equals by this definition. So this is technically -4 times -1, which would change to a +4. So even though we started with imaginary numbers, we had some i's in there, they should all conveniently go away, either by canceling or by replacing an I squared with a -1. Okay, all the i's should go away. Now, we're not exactly done yet, okay, because we still have more expanding to do, but now that all the i's are gone, I think it should be pretty straightforward. We're going to have to go through another FOIL process. And I don't think we have any more like terms to combine, so we'll just leave it the way it is. So just like we've been writing equations of polynomials up to this point by utilizing the x-intercepts, we can now do the same thing even if the x-intercepts are imaginary, okay, not graphable. We have to be careful though, because if they only give us one, it's up to us to figure out the buddy. Okay, what is the other imaginary number that would be associated with the one that they give us? Okay, we're going to try another one, just because I know this is a little new. All right, suppose that a polynomial function g of x has roots of x equals 1, which has a multiplicity of 2, and another root of 3 plus I. Can we think about what type of function this polynomial would be? Can we name it? What do you think, Lainey?
Would it be quintuple?
Why?
Because it has a multiplicity of 2.
Okay, so if we list the zeros, this one has a multiplicity of 2.
And then the I has
A buddy. So the one that they give us is 3 plus I. We'll assume the multiplicity is 1. They don't state otherwise. So what would the buddy be? Yeah?
X minus 3 plus I. Or like 3 plus I, or minus I.
3 minus I.
I
Good.
just solved it out.
You solved, yeah. Okay, so x equals 3 minus I. Good. Okay, so we have a multiplicity of 2, 1, and 1, so altogether that would be 4. Lainey, what did you say previously? Quartic. Okay, I thought you said quintic for some reason. Okay, so this would be quartic. Good. Because multiplicities add to 4. All right, let's see if we can figure out what this equation would be that would have these roots exactly. So we'll need, this should be an x equals 1. My bad. I wrote down the multiplicity instead of the root. So we would need x minus 1. How can we show multiplicity of 2? Squared. Good. Okay. Now, when it comes time to use the imaginary ones, notice how these imaginary roots have 2 parts, whereas the previous one we did just had 1 part. Okay, because the 0 wasn't there, we didn't have to really use it. So if we were to take x minus this, we have to subtract both pieces. So it's almost like distributing a negative. We'd have to make sure that we subtract the 3, but also subtract the I. We're going to do something similar for the buddy root. If we want x minus this 0 or root, we would need x minus 3, and then we're going to change it to a plus I. You got to subtract both parts. A little bit different than the previous one. So we have all the roots listed. Let's go ahead and expand it. Now, let's see. Maybe we'll go ahead and do the imaginary ones first, like we did previously. You can do these in any order you want, okay? Because you're technically multiplying everything together, so order doesn't matter. When you take a look at the imaginary ones, we have 3 terms times another 3 terms. So technically the FOIL process, first, outside, inside, last, is not going to work. You do, though, have to multiply everything in. So we're going to take x multiplied by the last factor, and then we'll do the same thing with negative 3, and then the same thing with negative I. So it's just a bunch of distribution. All right, so multiplying the x into everything, then the negative 3, then the negative I. There's a lot going on there, definitely. After you multiply everything in, we should anticipate every single I disappearing somehow, either by canceling out or replacing an I squared with a negative 1, like we did in the previous example. So can we start to cancel or combine some like terms? We're hoping all the I's go away. Do we see anything? Good, Olivia? All right, positive xi, negative xi, gone. Negative 3i, positive 3i, gone. Okay, so if I squared becomes negative 1, and we have the negative out front initially, that would double negative change to a positive. So we're left with x squared, and then minus 3x minus another 3x would be negative 6x. And then we'll be left with plus 9, and all of this became a plus 1. So in the end, we'll get plus 10. All the i's went away. Perfect. But we still haven't completely expanded it yet. We want to get rid of all parentheses. So maybe now we'll switch gears and try to expand this squared term. So this is really x minus 1 times another x minus 1. You're going to have to go through another FOIL process. And combining like terms, we'll have x squared minus 2x plus 1. So we expanded the x plus 1, we expanded the imaginaries, and now we just have to bring those together and multiply what's left. So we're still not quite done yet, but it's multiplication. I know it's stuff that you guys can do. It's just going to take some time, but I know we can do it. So more distribution. Let's bring in the x squared into everything, and then the negative 2x, and then the positive 1. Alright, so all the parentheses are gone, and then lastly we can probably just combine like terms. We just have 1x to the 4th, which is quartic, by the way, like we anticipated, so we know we're doing something right. Negative 3x cubed, negative 2x cubed, so negative 8. 10x squared, 12 and 1, so 23. Negative 20x and negative 6, so negative 26. Bless you. And then plus 10 on the end. There we go. Alright, so it's nothing terribly new here. We're just throwing in imaginary numbers to help us find an equation. It works the same way, just like we did with regular or real x-intercepts, but we just have to be careful with how the i's simplify when we start to expand it. Okay, we want the i's to go away. They're either going to cancel out, or you're going to have to use this property of I squared being negative 1 to help you get rid of that one. Are we doing okay? We sure? Okay. We're going to start the next section today, and we're kind of going to shy away just a little bit from positive, negative, 0, and imaginary. That's just a very vague description as to where x-intercepts are located. They're just telling us, are they on the right, are they on the left, are they at the origin, are they imaginary? What we're going to try to do in this next section is get more specific. So if we know that we have 2 positive x-intercepts, we're going to try to figure out where they are exactly. And I know we've used factoring as a method to help us find x-intercepts up to this point, but not every polynomial is factorable. So we're going to try to find a strategy or a method that we can use to, if that's the case. Okay, what if we can't factor it? How can we still figure out where some x-intercepts are located? So we're going to take a look at a simple quadratic to start things off, and then we'll get into like the quintics and the quartics and the cubics, okay, the higher powered. So I know if you were to look at this, you know where this is going? Where's this going?
Well, we're gonna like find all the roots and we're gonna synthetically divide them out of the equations.
I'm not going to make you synthetically divide all of them.
Okay.
Okay, we're going to use a calculator, but you're on the right track. Okay, so we've done this before. Maybe, okay. Which I'm pretty sure we've done this before because Mr. Konjak's doing it right now with his Algebra 2 class. So this is going to be, it might not be new. I'm not going to make you do everything if you know where this is going. But I know you've done this before. If I asked you to factor this quadratic, how would you do that? How can we get the little groupings? Can we think of a technique? Yeah? All right, AC. So 3 times negative 6 would be negative 18. B is 17. Can we think of 2 numbers that multiply to negative 18 but add to a positive 17? Yeah?
18 and negative
18, negative 1. All right, so from there, you would either do grouping or divide and slide, whatever your preference is. So it looks like this one is factorable, but we got to try to discuss what if it wasn't. Okay, how would we still be able to find x-intercepts? So this is where we're going to go over a different technique, okay, a different method. What we're going to try to do is list possible factors. Okay, we know this one's factorable, so we can get there immediately, but if it wasn't factorable, maybe we can list some possible ones. So if you think about factoring and how that's kind of related to the FOIL process, can we think about this in our heads? If you were to take this first term and this first term and multiply them together, what would you get in the standard form equation? The x squared. Okay, so in this case, 3x squared. If you were to take the last term times the last term, what would you get in the standard form? The constant, which in this case is negative 6. So what we can do is specifically look at the leading coefficient, okay, the number out front, and the constant term to help us figure out possible factors. Now, you only get the middle number when you have the exact combination, okay, the exact values that work, but just by looking at the first term and the last term, we can figure out some possible factors. So, let's go ahead and list some factors of 3, which is the leading coefficient. What are two numbers you can multiply together to get a positive 3? 1 and 3. What about some factors of negative 6, which was our constant term on the end? Two numbers that multiply together to get negative 6. 1 and 6. Okay, but that would be positive 6. All right, so the 1 could be negative and the 6 could be positive, or the 1 can be positive and the 6 could be negative. So maybe we'll throw in some pluses or minuses. Is there another combination? Yeah.
Plus or minus 2, plus or minus 2.
There we go. Okay, so if we can find the factors of the leading coefficient and then the factors of the constant term, we know that these numbers are the only possibilities that should be in these spots in the factors. Does that make sense? If we think about the FOIL process. Okay, so let's see what this could look like. We could have 1x in maybe our first factor, and that would mean we would need 3x in the other factor. If we multiply those first together, we'll get 3x squared. Maybe for the last terms, we'll do positive 1 and its related negative 6. That way we get a constant term of negative 6 when we multiply those together. So these are possible factors. I'm not saying they're the right ones, because we can eventually get there. We can factor this. But I'm just saying they're possible. So if this wasn't factorable, these are some possible factors that could be there. Okay, maybe some other ones are more difficult. That way you can't, that's why you probably can't do it using some of the techniques that we've discussed. But these are possible ones. Can we list some other ones? Some other combinations that can bring these together? The first terms have to multiply to 3x squared, and the last terms have to multiply to negative 6. Good, Lainey?
3x minus 1.
Okay.
And then
X plus 6. Definitely works. 3x times x, 3x squared, negative 1 times 6, negative x. Notice how these two factors are different than the ones that we listed above. So we should be able to fill out the rest of these. Can we find some other possible factors? Yeah?
Would x minus 1 and 3x plus 6 be different?
Yep.
That's wonderful.
That's different. It's related to this one, right? But it's different. So it's a different possibility. The first still multiply with what we need it to, and so do the lasts. So we're good. Can we find some more? Let's see, if we do something similar to what Travis just did, we can do 3x plus 1 and x minus 6. That's similar to the second one we wrote, but it's still a different combination. Can we find any more? I see pencils moving. I'm curious with what we're writing. What did we find? Go ahead, Elsie. Yeah. All right, that one would work. So if we wrote the similar one, we could do x minus 2, 3x plus 3. There should be one more set. 2 more left. Yeah?
X minus 3 times 3x plus 4.
All right, so then the other one would be x plus 3, 3x minus 2. Looks good. Okay, so again, these are possible factors. One of these is the correct one if you actually did this A times C technique, and we'll see which one that is in a second. But if these are the possible factors, can we write the possible roots? Right? If x plus 1 is a possible factor, then x equals negative 1 would be a possible root. And then if 3x minus 6 is a factor, then 2 would be a possible root. We got to figure out what makes each individual factor equal to 0. So if we go through the other ones, we can get 1/3 and negative 6. 1, negative 2. Negative 1/3, positive 6. Negative 2 and 1. 2 and negative 1. 3 and negative 2/3. Negative 3 and positive 2/3. So assuming, okay, we'll make this assumption for a second. Assuming that our original equation was not factorable, if these are possible factors, okay, there might be other ones that are imaginary or maybe more difficult that we can't think of, these would be some possible roots. Now this one was factorable. So can we take a look at all these different options, and if you were to do the outside and inside portion, they would have to add together to 17. Can we put a star next to the one that's actually correct since we can factor this one? Can we find it? For instance, the first one, if we did outsides, that would be negative 6x. Insides would be 3x. Added together would be negative 3x. And we want to get a positive 17. Can we find the correct pair? Can we find it? Yeah? So the second one? Okay, so outsides would be 18x, insides negative 1x, so 18 minus 1, 17. All right. So this is if you were to actually factor it using this A times C technique, it would eventually lead you here, which means the actual zeros are 1/3 and negative 6. This one's nice because we were able to factor it, but tomorrow we're going to take a look at ones that we can't factor. Would you agree that this was kind of tedious? Yes, we're going to shorten it up tomorrow. Okay, we're going to take a look at a quicker way to eventually get to where the possible roots are located.